Welcome back. So now we are going bit to the technical after a dreamy start by Damien. So, so today second session is basically wettability switching. And it's the right time to have a discussion about the wettability, right? Because heavily raining, huh? And many are from outside of Kerala. So enjoy your lightning, thunder, and all the things. Yeah. So a skeleton, we may not strictly follow this one, don't need to follow. But skeleton is, we should have an introduction about the wettability, what is wettability, what is the importance. Then some fundamentals, it's not going to very deep, but some fundamentals of wetting and some fabrication strategies. Then, like Damien told in the first, understanding, designing, programmability. This is how it goes for the soft matter, right? So I will also try with my level to follow his guidelines. Okay. So then some applications and see what we can do. And this course is, this session is important for your laboratory session. There is one laboratory session on wettability, measurements and all. So this can be acting as a guidelines for that. Okay. So let us start with anyone is working with wettability, contact angle measurements from Christ University. Okay, Vinod sir. Okay. Then Banu is there. He is my first MTech student. Now he completed PhD from IIT Kharagpur, Suman Chakravarti. So as per the philosophy of research and PhD, he definitely knows better than me. Okay, this is how it works. Okay, with that introduction, let us go to the contents. Okay. So you might have seen, I'm bringing some leaves. Damien is a fan of nature, so I did postdoc with him. Automatically, spreading will happen, right? So I'm also a bit of fan of nature. So we have got some sort of different kinds of leaves. And first 5 minutes, I will request to some of you, because we are going to discuss about the interaction of water with the surfaces. That's all about wettability, wetting, right? That means this water droplet, when we hang a very small droplet, it appears to be spherical, right? Right? And when it goes to a surface, it takes the definite shapes, right? How it takes the definite shape? He senses it. It's like he is behaving like a living creature, right? Right? So what he senses and how he reorganize according to the environment. There should be something governing laws, right? Governing rules, right? Otherwise, it will be completely random, right? It is not like that, right? And some specific, any examples you can give me, like, nature, to convince that nature is the best, the wettability engineer or designer or scientist, whatever. We learn everything from nature. We try to mimic a 1 or less than 1% of what is happening in nature, right? So any examples to start with? Lotus leaf. What is lotus leaf? Super hydrophobic. So why nature made lotus leaf super hydrophobic? There should be a motivation for nature to do that, right? That's an interesting question, right? Why nature did it? Or it's a part of evolution, right? We are not saying, okay, nature, okay, next day onwards you behave like a super hydro. It's not happening like that. It's a part of evolution, right? We are also at this stage because of evolution. After 1 lakh years, we don't know. Banu will be sitting, Banu's juniors will be like this shape. We don't know. Right? Soft matter, that's the advantage, right? You can sense the environment and modulate yourself, right? So why nature made this one super hydro? It's a good question, right? So let us keep that question now, because we are going to the details, right? If you have some answers now, we can take it.
I think a leaf has to perform photosynthesis, it's quite large. If water get stuck into the leaf, so it will retard the process of it should be clean to have the absorption of light for the photosystems. So it need to be get away from the major
So it
surface
should
area should be
repel water
yes.
to keep its sensor on the surface
yes.
of water, right? Otherwise, if you imagine like it collects a lot of water, it will sink, right?
Yes.
It can pierce off. So, and it should survive, right? It's basically, if water layer forms, the fungus, it's all kind of dirts can accumulate and it will kills all the functionality you mentioned, right? Then in desert, some sort of beets, some insects, in desert, how they get water? Some plants, some insects, they have very specific wettability designs, right? Because they should, because the collection of water is not from rain, right? It's from the humidity, or it should condense, but not only condensing, it should collect, because there will be some region you have to collect, right? Like a lotus leaf, any other leaves you can give me examples? Rose petals, okay. So rose petal and lotus leaves. So what is actually what you want to?
The microstructures of how is actually different
Mhm.
and leads to different behavior in those cases.
Yes, Yogesh, we are faculties. Yes, both are faculties. So we will not go to the technical details at this stage. And as a bachelor level or master level student, what exactly we feel the difference? As a we are going to first year BTech students. Sorry, we are friends. So I this framing. So if you think about the lotus and the rose petal, both are hydrophobic, to an extent super hydrophobic. I hope Banu also will agree with me. But in the case of lotus, what are rolls are? Rolls away, right? Do we have some demonstration to show that? No need of lotus, but some super hydrophobic? Yes. Please take that. Okay? But in the case of rose, as Yogesh sir rightly mentioned, because of some properties, it is remaining super hydrophobic, but water sticks on the surface. That means it is super hydrophobic, it sticks on the surface. That means super hydrophobicity alone is not deciding whether it is droplet need to be transported or not, right? Something else need to be understood in between. Okay, with that surprise, let us start the slides, right? So because I have, because I am supporting Damien, so I have only 1 hour. Okay. So, geographically we are placed in one of the best locations, right? One side we have mountain, I will call it as a hard matter. There are many soft matter on the hard matter. Okay. On the other side, we have beautiful beach, right? So basically, it's a soft matter, right? Damien already showed you beautiful videos about it. It's all coincidence, okay? There was no discussion about the contents of the videos, so it happens. And we are actually in the transition, right? Hard to soft transition. In terms of weather, in terms of geography, in terms of, the roads, everything, we are in the transition. So we have to modulate ourselves every day like a living. So with that context, let us start. About myself, I am skipping. And about my lab, this is a beautiful emblem one of our master student developed. So you can see it covers everything what we do. We have drops, we have bubbles, we have light, we have emissions, plasmonics, heating. We put everything to disturb soft matter systems. Okay, and ask them to do some functionalities. This is what our students are doing. Okay, my beautiful team, some are have completed PhD already, doing jobs, others are still around, and some of the publications from us. Okay, so let us start with this slide. Okay, so the interaction of water or the drop, let us say, with the surface decides, right? So then the question is what property this water is actually feeling once it drops, right? Okay. I will start with one beautiful leaf. Duty of rose is already over. So you see, it's rose petal, but it's not connected to his parent, so he is tired. So it affects his performance also. But some assumptions we have to do, right? So it's not super hydrophobic. The reason I already told you. Some part it is super hydrophobic. But it tried to stick, right? Because we have a feeling that, if it is super hydrophobic, it should roll off, right? Yeah. So petal also have some sort of properties, but anyway, it is not really reflecting, right? But the point I want to say is super hydrophobic, it is not rolling off, right? Then this is super hydrophobic, right? So this is super hydrophobic coating, right? So you take this one. Jump. Now you take a petal also. Maybe that petal also will work. ഒന്നും എടുക്കാൻ. Yeah. It gets stuck, right? You see? It's super hydrophobic, right? But it gets stuck, right? It's very difficult, right? That means up to 70 degree, 80 degree, I have to tilt it, right? And now I will show you another one. It's very common in our place, right? So, I hope it's clear, right? So there in any direction I can do it, right? So here I am putting a drop. You see it takes an anisotropic shape, right? Got the point? And if I try to put it in this direction, the water is not rolling off, right? Agree or not? But in this direction, it will be very easy. It starts to move, right? Got the point? Because there are grooves, right? There are channels to guide, right? So the nature is actually doing this on purpose, right? Because it is now, it's actually to collect water, direct water in specific directions, right? Okay, so then with the lotus leaf, we see we have super hydrophobicity, right? The second case, the rose petal, Banu corrected me, thank you for that. And it is super hydrophobic, but it is actually having somehow friction is there, right? It stays there, right? Somehow it's not easy to move. And anisotropic wetting, right? And the third image is actually leaves, right? It can be rice leaves or this leaves. It is having some directionality. Nature gave some directionality, right? Water cannot overcome the barrier in one direction. In the other side, it is easy to move. And the one we see in the desert is our all microstructured surface. And once the droplet get condensed, there will be grooves like this, right? There will be grooves like this. It will direct the droplet to certain region, right? It's very interesting. For condensation also you need structures, right? So the nature is somehow engineered the structure, the organism very, very well. Okay? So our job here is, some have already worked with wettabilities, others are new to wettability, even though every day we are doing, right? We are using water, right? Different ways we use water. So now onwards, you try to appreciate how the water drop behaves. Okay? Okay, so we will start with how we can understand it. Okay? What are the deciding factors? To start with, if you think about interaction of water with the surface, can you tell me what are the possible reasons? What are the possible reasons? You don't need to take a photograph. We will give you the slides, okay? Don't worry about that. Let us have a discussion here. You will get the material. Huh? So what are the possible ways this drop can interact with the surface. Surface tension, how? Because now I am saying about an interaction, right? Huh? Cohesive forces, interfacial tension.
It can stay, it can get absorbed, and it can stay based on the surface energy of the
surface energy. Okay. So I would categorize into two simple terms. One way is physically, right? Because he can actually sense the structures, right? I told you about the grooves, right? The other ways you can have some sort of a chemical interactions, right? So in most of the cases, both are existing. In nature, it's actually a smart combination of everything. In lotus leaf also, like, you have very good structures, some wax coating is also present. Okay? So generally we categorize into two, physical and chemical. And we try to mimic. That is what the smart wettable surfaces do. Okay, we try to mimic what is there in the nature and we apply some external stimuli to, because it will be in a balanced situation, right? We have to apply the balance to disturb the balance. Then the droplet will behave to compensate what I did against it, right? That will lead to a motion or spreading. This is the fundamental thing. Okay. So to understand that, we need to understand some very basics. How we characterize or how we categorize the surfaces. So this is our starting point. So the motivation is clear, right? So why we need to understand the wettability properties on the way we will understand, and some motivation already taken out. And can you tell me some important applications before going to some textbook materials? Wettability will be affecting the dynamics. Some specific application, can you tell me? Printing, yes. Phase separation, okay, bit deeper. Yes. Waterproof material, that means, if you take a car, I would like to have, always super hydrophobic, right? But somehow it's not easy. Then, self-cleaning. Even in flights, we need, this kind of materials, right? The drag, a lot of interesting things are there, right? So the world around you is very, very huge. Starting from printing, who told that? It's a good starting point to aerodynamics. The wettability properties are super important, okay? So with that, let us start some fundamentals. Anyone heard about contact angle? Everyone. So what is contact angle then? We put a droplet. So when we put a droplet, is there any condition you have to think about? If I pour a bucket of water, or mug of water, take a mug and pour it, whether I can measure the contact angle? Why? Because being an experimentalist is basically you should know how to do the experiment, right? Drop of water. Why? What is the typical quantification you say? What should be, because if you want to measure the contact angle, for example, okay? So whether you take 1 liter of water or 1 nanoliter of water, that is my question. I would say surface tension should be dominant, right? Because if you have a large paddle of water, the gravity will be having impact on that, right? So I will take something like 2 microliter to 10 microliter. It's okay, Banu? Yeah. To measure the contact angle so that I will get a decent idea about the measurement of the contact angle, right? So as somebody told, okay, we have to put a drop and the drop will take different shapes. We have already seen different shapes, right? In the case of that rot's leaf, it was spreading. Okay, in the petal, it was super hydrophobic, but it was somehow sticking. In the case of that lotus, it should be spherical, right? And it easily rolls off, right? So how it happens? And based on that, there is no cut and hard boundary like 89 to 90 is the transition for hydrophobic, nothing like that. But to have a visualization, have a processing easier for the brain, we have actually, if it is below 90 degree, we say hydrophilic. And if it is like, 15 degree, 10 degree, we say super hydrophilic. Because, there are super spreaders, right? There are some surfactant systems which spread like anything, right? Super spreaders. And some leaves, water, if you normal water also can spread. Okay? So super hydrophilic, and typically between 90 degrees to 130, 140 degrees, we say hydrophobic. Okay? Doesn't love water. Okay? Then extreme case comes. Okay? Above 140, 150 degree, we are saying super hydrophobic. Okay? It's not loving water at all. Okay? It's about to repel, right? So the point is, if you think about the dynamics, if you think about the transport applications, which one you will choose for transport applications? There are 2 lectures in this lecture series. One is on solid surfaces, like the wettability we are going to discuss. Couple of days later, I will discuss about slippery surfaces, another class of beautiful smart material having amazing wettability properties. Okay, it can be categorized into at least 3 categories: hydrophilic, hydrophobic, and super hydrophobic. Extremes are always possible. So then, how the drop sends this one? A very basic explanation. You see, a droplet is placed on the surface, right? And what are the interactions happening there? Because if you think about surface energy, for example, there are solid liquid, right? Because there is a contact between solid and liquid, and there is a contact between liquid and gas, right? Like liquid air, right? And there is another called the solid and gas, right? At the 3-phase contact line, that the point where they meet, drop has to take a decision, right? What shape, how I will balance this one, right? So then this equation decides you what will be the contact angle you can get. Okay? Because if you think about the vector directions, you will get gamma Sg is equal to gamma Sl plus gamma Lg into cos theta c. That theta c can give you an idea about the wettability properties, and you can think about connecting to the previous slide in which category you will put them, right? So here the issue is, this is a highly idealistic situation, right? Highly idealistic situation. This is not taking into account any sort of, the roughness, it's all smooth. We put a drop and behave, right? So, and this is called an equilibrium contact angle because the droplet takes an equilibrium shape, okay? But in reality, we are, okay, there are some surfaces which can actually give you equilibrium contact angle, but most of the surfaces are like, not really following this one. One example is to show that, like if you take a drop, okay, if you take a drop and I put it like this, okay, it's pretty nice. And if I put a drop, slightly with the higher Weber number, higher energy, spreads more. Okay, the change I did is very, very small, right? Similarly, I change the volume a bit. It's not having, if I try to measure, I will get different numbers, right? Same surface, same water. That means, somewhere we have to do a correction, right? It's not the right way. But if it is having an ideal surface, we'll follow that. It's not happening. Okay. If you increase height too much, okay, the energy gets too much and it can spread. Okay, but I am saying within that tolerance limits itself, it can actually lead to some different values. So then we have to modulate ourselves to have a broader picture about the contact angle in a practical sense. Okay. So this is called a static and dynamic contact angle. Let us take the case of a dynamic contact angle. I will tell you what it happens. Okay. With a board, it is better for me. I hope it is visible to everyone, right? So you put a drop here, okay? And it will take a shape like this. I am calling it as a static contact angle, okay, or equilibrium contact angle, okay? So now, let us do a hypothetical experiment. We will do that in the lab. Hysteresis measurement we are doing in the lab, right? Let us think about putting a very thin needle to it and increasing the volume of the droplet. Okay? I hope everyone is following that experiment, right? So if I increase the volume, what is going to happen? If it is ideal, it should spread in such a way that theta S is constant, right? Because in the previous expression, I haven't added any volume. This is the surface energy balance, right? Agree? It should spread in such a way that, but in most of the surfaces, it will not happen like that. Okay? Most of the surfaces, what will happen is like, if you increase the volume, the contact angle will increase. The contact angle will increase to a certain value. After that, it will start. This is advancing contact angle. Okay? This is practically a repeatable measure, right? We can actually repeat in homogeneous surfaces as well. Okay? Because it takes care all the things on the surface. Okay? Then that is one parameter we call advancing contact angle. Okay? There is another one, because we should know this is about spreading, right? Expanding it, right? We need to take out the drop also from the surface, right? Agree with me? Because we are putting a drop, we should know how it will be moving. Similarly, I should know how I can withdraw it right from the surface. It's important, equally important. So I can actually apply the reverse pressure to take out the liquid, right? And if it is an ideal situation, I told you this theta S exists, it will be keeping this theta S constant so that it will spread randomly. But here what is going to happen is, it will not follow this one. And at a lower contact angle, then only it will start to recede. Okay? I drawn it in an extreme case to convince you. Okay? It is not like this in all cases, but I am saying. Okay? And this angle is called receding contact angle. Okay? That means you have an advancing contact angle and you have a receding contact angle. Okay? And this will be highly reproducible. Nearly reproducible. But still there will be an error, because how to put the drop, anisotropy of the surface, everything matters. That is why in experiments we do give error bar, right? Like 10 experiments you do, calculate the standard deviation and give realistically how the surface behaves, we give. And these, the difference between them is very important for me, right? Now I will connect with these examples. So now I have two drops. This can be done in another way. I will do that. Okay. So now I take a droplet, put a droplet. Okay. This is having theta S. I am saying for the moment, static. Now I try to tilt it. So in the previous case, I added the volume, right? I push the three-phase contact line to respond to me, right? Now I am tilting. In tilting, what happens? When I tilt, the gravity is there, right? It is not like a nanoliter droplet, right? It's like some microliter droplet I am putting, right? And then, what will happen? It will acquire a shape like this, right? Before it starts to move. Here again, I am taking a caution. If both are same, it will start immediately when I try to tilt, right? But in reality, it takes time or takes angle to do that, right? You can see a droplet in an anisotropic state. Anisotropic state means, in one axis it is having more spreading, the other axis it is having less spreading. And you see, I try to tilt, right? When I tilt, the shape is exactly what I have drawn there, right? And if I increase further, I hope it is clear, right? If I increase further, the droplet starts to slide, right? It starts to slide and it's going down now, right? And there they will maintain that difference. Got the point? So in this way also, you can actually measure the advancing contact angle and receding contact angle, and depending on the surfaces, it's having superhydrophobic or hydrophilic, you can choose which method works better for you, okay? So the difference between is called hysteresis contact angle. So basically, the difference gives you the hysteresis. Okay, and this is very important property when you think about the transport, because in microfluidics I need a manipulation of droplets. I need to transport, right? So for transport application, I need to overcome this, right? Hysteresis is actually a frictional thing which actually resists the motion of the droplet, right? We need to understand how the hysteresis works. I hope up to this point it's clear, right? So we are putting a droplet and a highly idealistic situation. Both the surfaces have the equal contact, both sides are equal contact angle. And when I tilt, system keeps the contact angle same and slide, I would say. Okay? But in reality, what we have seen is basically it's not happening like that, right? The drop actually changes its shape before sliding, right? That means something interesting is there in between, right? That's what the hysteresis will give. Hysteresis value will help us to understand how the material behaves. Now you remember, you will be able to connect. This is actually a kind of analogy of lotus leaf, but chemical, right? Yeah, it's a chemical version of lotus leaf. You can see, I am trying to keep it at very horizontal, right? My hand is shaking, vibrating, is there, natural frequency is very high. Okay, so, but still, it rolls off, right? You do this experiment to convince that I am not doing any manipulations, okay? In her colors also it rolls off, okay? This is what a lotus does, okay? Now, in the case of this one, okay? Yeah, I hope he will respond to me happily, okay? Yeah, good. So here also it is hydrophobic. It's not super hydrophobic, very high contact angle should be there. But you see, then now it starts. So super hydrophobicity is not the only measure which decides the transport applications, right? You have to think about the contact angle. I hope I am able to convince you. Now, in one more way, you see, now you take this leaf. Now onwards, after this lecture, hopefully after this, the whole seminar series, you will be appreciating the nature better, respecting the nature better, hopefully. That is the first aim we have, okay? So you take this one, and let us put a droplet here, okay? Or you do an experiment. You are in a very unstable, energetically unstable seat you are sitting, okay? So, okay? You put a drop there. Okay, now what I am going to say is, you try, there are grooves, right? You try like this. Go to your extreme. Go to your again. It's there. Even gravity is not able to pull it down, right? Now the other axis. Yes. It will slowly start to move, right? Agree or not? That means in one axis, the droplet feels very high friction, right? It's not able to move, right? That means it is actually, nature is actually confining the droplet to move in only in specific directions. This is very important, right? See how beautifully and in nature it's very interesting, you see. When when the drop forms and some wind will be there. Nature is very cleverful, right? And if we put this one, the weight also will act in this way so that the droplet will go here. And then he will follow this path because this is having a groove going down so that he will ensure that the roots will his root will get the water. Now you think about engineer very bad. So that he makes lotus leaf this. Okay? Lotus kind of design you did. What is going to happen? When the droplet comes, it will jump away from you. So you see, you are actually losing, right? So the nature actually does the things very in a clever manner. Okay, this is what I wanted to tell you. Okay. Now some slides which will be connecting all the things. Okay, I hope I can quickly go through these slides now, right? This is the illustrations because I have to give you the materials, right? So in the slides it will be there, advancing contact angle, receding contact angle, and how it works. I hope it is self-explanatory now. Theta A minus theta R, the hysteresis contact angle. Okay, and one more parameter we can incorporate is the spreading parameter, which basically rearranging this one to say whether the droplet will spread on the surface, how fast it will spread, all the things. Okay, so you can see a complete spread wetting is like super hydrophilic, right? It goes. So it's all a rearrangement to get to understand how the surface interacts with the liquid. That means this energy balance, that's what we are our concluding point, right? Basically the drop sends how I want to interact with this surface chemically and physically. Okay? Then a shape it takes, right? Which satisfy. Okay, there I can sit, means energetically favorable state, right? This is it's like exactly like a living creature does, right? So the droplet is one of the best example of the living creature. Okay, so yeah, I will not go to, but Damien will go anyway, so I will not kill the surprise. Okay, so the question is how we can measure, right? The very simple technique. Okay, very simple technique. You put a drop and you put a camera, one light source, measure it. Okay, and then measure the contact angle. One is actually a wettable. That is actually a hydrophilic or hydrophobic or super hydrophobic. What kind of surface it is? It is it is hydrophilic. Angle is written there. I should have removed that. Okay, it is hydrophilic. Okay. So then, in certain situations, and in this one, basically, you can actually do everything, right? You can add water, then you see how the contact angle varies, measure the advancing, receding, or you tilt. We will be doing these both experiments in the lab today. Some group will be doing today. Then by the end of your course, everyone will be doing this, okay? So advancing, receding, even surface tension, you can measure, okay? So then certain situations, it is especially when the contact angle becomes very, very, very small, like less than 10 degrees. This is a shadowgraphy technique, right? How a shadowgraphy technique works? We are taking a shadow of the drop, right? Nothing more than that, right? So if the contact angle getting decreased, it is very difficult because you need to fit, right? Whether it is a tangent fit or circle fit, you have to fit to something, right? For that you need a kind of, the contrast should be very high, and you need to see the change, right? But if it is a very small contact angle, it is very difficult, right? Because it will be having very small, otherwise you have to use very high magnification optical systems, right? So then it gets difficult. So then in certain extreme applications, I am not saying the one I am going to show in the next slide is a commonly used one. If you want a very precise measurement, since we have to obey the copyright because it's going to be streamlined and recorded. So we are restricting ourselves to be in our own material, like from our lab, okay, maximum. Otherwise, citations are given. So in a collaborative work with Dilip last year, we used interferometry, okay? So interferometry and fringe projection method. So the working principle is very simple, okay? Here now you are not directly measuring the contact angle, you are actually measuring how the refraction, how the beam bends when when it goes through droplet. That is actually a measure of the curvature, right? Gautam, when you think about a lens, it focuses, right? That means, tracing that path of the beam, you can find out the curvature, right? That basically will give you the contact angle, the focal length, right? That means if you know the focal length, you know the contact angle, right? Assuming no aberration is there, okay? It's not exactly like that in the case of drop because, because of the Laplace pressure towards the edge, it is not exactly followed, but some simplification we have to do, approximations. So here the principle is, I hope everyone is able to see this, right? So with a Mach center interferometer, it's a Mach center interferometer, we produce fringes, parallel fringes, right? So if you have any doubt, you can actually discuss with Ardra. She was doing the images, which I will show in the next slide. We will get a parallel fringes. You can do other interferometric techniques also to make parallel fringes. The approach is very simple. If there is no distractions, it will be parallel, right? And if you put a droplet in one of the arm, you can see a droplet sitting in one of the arm, right? And when we see from the bottom, the fringes will be deformed, right? Fringes will be deformed in accordance with the curvature, right? That means that is a precise way of measuring it, right? And in the next slide, you can see some droplet evaporation in the case of 0 seconds. You can see the fringes are bended inward, right? Exactly like the simulation you have seen in the previous slide, right? And towards the end, you can see it is flat, right? About to dry, right? So that means it gives a more microscopic information about the contact angle. And this you can translate, okay? Because if you know the refractive index, if you know the other parameters, you can do a calibration curve, how much bends corresponds to how much contact angle. So it's a very precise method. We published that in Langmuir. Dilip, he was actually working with a very low contact angle systems and it was really successful. We did it in our lab and we did a setup in IIT Madras also. Yeah. So then, all the things we have told now, I will summarize put it under different categories. We mentioned about the lotus, rose petals, right? He is having high contact angle, but high hysteresis as well, right? You are not, the droplet is not moving around it, means high hysteresis, right? How it happens is, these are all microstructured surfaces, When you put a droplet, it goes to these, the grooves. Got the point? That means, you have a more contact area, right? More surface area. That means more surface area means more interaction, right? But the contact angle remains high. But still you have more contact area, right? Contact angle. Interactions, I put it in that way. That means even though superhydrophobicity is achieved in this case, your drop is not moving. That is what Rose want, right? He don't want the droplet to simply bounce off, right? He want to collect it. Then after it grows, gravity will pull it down, right? So he will get his part. It's clear up to now? Now the other extreme case, our lotus. Banu, you remember these images? The bottom one, right? So this is the extreme case. What happens is, you have a specific pitch you have to satisfy and some materials, it is not obvious to get Wenzel and Casey. You can have a transition from this depending on the volume, surface tension of the droplet and all. We cannot simply say one surface is Casey for every liquid, no way, okay? You can see, it is like, there's the second figure, if you follow the second figure, it is actually like, sitting on the droplet without going inside, right? That means there is an air packet formed, right? Along with that, the surface area, contact area is getting significantly reduced, right? That gives you, because we already understood chemical and physical interaction effectively leads to your hysteresis, right? And here the hysteresis will be very, very, very less, right? Because the contact area it forms is very, very small. And such states are called Casey-Baxter state. The previous case is Wenzel state, and classical example for Wenzel is our rose petal, and Casey-Baxter is our lotus leaf. I hope up to now things are clear. Okay? So targeting an MSc level student, higher slightly beginner of PhD level student. I hope any questions up to now, because it's already 1:15, already 1 hour over. So, but still 10-15 minutes I will continue. Okay, then we will go for lunch. So these are fundamentals. Okay, when you start working with the droplets, these are the fundamental things you have to understand. Okay, up to now everything is clear. Okay. Now isotropic wetting, anisotropic wetting, already example is clear, right? Anisotropic wetting, that is why we have taken beautiful leaves, so which demonstrates so that it is already working, right? Now we just need to put it in slides to explain it, right? So anisotropic wetting, it tells you that there will be some confinement in certain direction, right? He has to give more energy to overcome that, but there will be some easier path to follow. So the nature always goes for the easier path, right? So it will translate or it will transport along that. Okay, this is one passive way of guiding the droplet, right? So these are passive way, because the nature is actually not changing the patterns, right? The pattern is fixed, right? Agree? So passive way. But there are some active waves also, because by modulating the energies, the forces. Okay? So then one fabrication approach which is classical is the soft lithography. Okay? Soft lithography approach. When you have any samples with you now? Okay, if you have, you can take, otherwise later. Okay, anyway, lab session is coming. Here what? I will quickly explain this procedure, okay? So you think about the first one is lotus leaf. I want to make a number of lotus leaf without disturbing nature. That means I have to replicate it, right? That is the purpose, okay? So then PDMS is the best friend for us, so that he can actually cure and he can actually goes to even close to nanometer structures, okay? Applying some vacuum, we can get rid of the bubbles and then heat it, okay? Heat it at certain temperature, 80 degree, 70 degree, you can actually get the negative. You remember this one, right? Got the point. And you can do it over that, right? So you have a lotus leaf, you put the PDMS, you will get the negative, right? Then that negative can be converted to positive, right? That means you apply a non-adhesive layer on the negative and do it again. The baby will be positive, right? So 1 and 3 will be identical. Grandfather and that is why they have, in life also we have more interaction, more, the connection between the 1 and 3, right? Maybe nature also does like that, right? Okay, fine. So this is what Banu actually did it in the lab. And another approach is basically laser microstructuring, because you can on glass, polymer surface, we can actually inscribe structures. Okay, you can using laser you can locally burn, right? That means you can locally write the structures, very beautiful structures, and all this information is there in our ACS applied materials interface paper. Whoever want to read can follow that. Then the question is, we have already understood one way of transporting the droplet, right? That is gravity, right? Whatever we have done till now is without gravity it will not work, right? We tilt means one side it pulls. Who pulls? Mother pulls. Okay. So then, without that, in real applications, it is difficult to tilt, right? What about modulating the forces? That is the question. Okay. Let us see. So this is one anisotropic structure we have fabricated and published recently in Colloids and Surfaces A. You can see this kind of a triangular structures, right? So if you put a droplet, okay, so that is basically a super hydrophobic. The white structures you are seeing are super hydrophobic. Okay? Then if I put droplets in a slightly tilted angle, how the droplet will move? He will follow that directions, right, to extent possible to avoid these hydrophilic regions, so that towards the end he will try to accumulate, right? So this is what the beetle structure in the desert, right, does this one. Okay, he will be having this kind of grooves, and the advantage with this one is once it reaches to the other side, because that also you need to take care, right? Because if it is like a groove and towards the end it will roll off to the soil, whatever the effort he does is gone, right? He does this very carefully in such a way that towards the end there is actually this hydrophobic regions are getting smaller and hydrophilic regions are getting higher. So that once it reaches to that towards that contact points, edges, hydrophilic parts takes care of that. The droplet gets stuck there. Then the gravity will give he can drink. Got the point. So this, like we are trying to mimic what is there. And it's a very beautiful way, and we recently got it published. Very simple. One bachelor student, others did it. We got it in a very high impact. Okay. So this one is with wettability gradient. You can see a droplet is placed and a high-speed video. You can see he really senses, right? You know, see the beauty, right? He really senses and moves towards one direction, right? It is flat. It is perfectly flat. There is no gravity place. And he actually jumps and moves towards one side. How it moves towards one side is very interesting, right? This is by applying wettability gradient. You can note down that word. Yeah, so if you think about such a system, let us write two forces acting on the droplet, right? Assuming all other things are not taken into account. Okay. So first one is because of the variation in contact angle on either droplets, right? So wettability gradient. What is the easiest way to understand wettability gradient surface? So wettability gradient surface is okay. This may be theta 1 and theta 2. I would say theta 2 is greater than theta 1. Then if I put a droplet, in which direction it will move? Theta 2 is higher than theta 1. In which direction it will move? Towards theta 2 or towards theta 1? Towards theta 1. Very good. Always it will move? Answer you told is if it moves, it will move only to theta 1. Okay? Other question is whether it will move always. The question is clear, right? I have a wettability gradient surface having a significant contrast in wettability. I put a droplet, definitely there will be theta 1 will be different to theta 2. Theta 1 will be like towards wettable, it will be spreading more. Perfectly okay. The question is whether the droplet will move automatically. Respond. So, Damien told our awards are waiting, right? These are the questions which will decide, you know. Without that also we don't need to even go to Cassie and Wenzel to do this. You are saying as the time progresses, it can move. Definitely time should progress. There will be a region, there will be a state, right? It cannot further change it. Because I told you, basically, we are changing surface roughness or chemical, right? Both ways you can make a gradient, right? But there will be a limit, right? So the answer is, it will not move always. It will spread always. I hope the difference is clear, right? It will spread always and it will make like, you know, the gradient shape. But it basically will not move always. To move always, you need to overcome the hysteresis forces. Okay? It actually tells you about the advancing and receding contact angle, right? So the droplet to transport over a surface, what are the criteria? You need to have wettability contrast, wettability gradient, and on that surface, that wettability contrast you develop or generate should overcome, translate in terms of forces, right? Wettability gradient forces using that expression. And it should overcome the hysteresis, friction, right? You put a rope and you have to overcome that to move. So these are the two criteria you have to think if you want to transport. In between, if you just want to spread in certain sub-application, you just need to spread, fine. Then you make a surface having high hysteresis. So our design criteria. I hope you understand about this, the role of these equations, right? Now, these are all not dynamic, again passive. I am quoting with some nanoparticles to make these structures. Now what Banu did is very clever. He used a smart polymer surface called the pinipalm, who can actually respond to the temperature. And so liquid LCST is there at around room temperature, right? 30 to 32 degrees. So that he will be from hydrophilic to hydrophobic. So the point is, if you can actually translate this temperature and connect with the contact angle, you can actually realize this gradient, right? Then we started that experiment in 2016, and we started with the PDMS layer, the first one. You can see at two temperature, the first one is lower and the second one should be higher, right? Banu? Yes, while cropping we missed that. Okay, but no problem. So on the left is basically at a low temperature, something like room temperature. The right is basically 40 degrees, for example. You see there is a contact angle increase, right? Because he is becoming more enemy of water. Okay, but you see the hysteresis or a tilt angle approach we did it here. You can see even at 40 degrees, very close to 40 degree. That means, the droplet will not move, right? You have to tilt it up to 40 degrees, right? That is not a useful surface, right? Then we actually did a very interesting experiment. That's what basically your transition between Cassie Wenzel will come there. And we actually made a, where is that? Yeah, structured surface using laser printing. And there basically, Cassie to Wenzel is happening. Above room temperature 32 degrees, it will be super hydrophobic. And if it is below LCST, below 30 degrees, it will be really hydrophilic, right? It is well below the PDMS contact angle. That means you get a gradient of how much? 100 degrees. That is a huge number, right? 100 degrees contrast you are getting between a temperature gradient of 5 degrees. Everyone is following or not? Now our next aim, what will be our next aim? Being an experimentalist. Now we understood, we got a material, right? So what, to have a transport application, what will be our next aim? What we will do? I want to transport droplet controllably. What I will do now? So I know this material is behaving very well with the temperature, right? If temperature is slightly above room temperature, he is super hydrophobic. Below, okay, it is not super hydrophilic, it's very good hydrophilic surface, right? So if I want to transport, the first condition I achieved, right? Huge change in contact angle, right? Next one is basically I have to check how the hysteresis works, right? That's also equally important. You see that image, even very close to 1 degree at high temperature, it actually rolls off. That means the hysteresis is very, very, very small, right? When it achieves, that means it really proves that it is in Cassie state. Okay? So then, yeah. So in this condition, we have to apply a, I have to go a bit quickly now. So I have to apply a temperature gradient to achieve this one, right? So let us see how the drop feels when you put, yeah, this is what the poor droplet feels, right? When I apply a temperature gradient, right? So you have actually a surface having low contact angle on this side, high contact angle on the other side, temperature T1, T2 is greater than T1, all these conditions you have to put in line with the measurements you did for temperature. Then the droplet basically should move in this direction. The forces acting are, you have wettability gradient, contact angle gradient, and a Marangoni. What is how the Marangoni comes? Because of the surface tension, okay? Because you are changing the temperature means the surface tension is also changing. That also have a contribution in the contact angle, droplet flows, and all beautiful physics is there, okay? So then The direction, if you take the wettability and Marangoni are actually nearly in the same direction, the other one, hysteresis, definitely will act against it, right? So you have to understand which one dominates. That means you have to work for analyze in terms of forces, right? Because now three forces, instead of two forces, here three forces comes into play, right? Let us see. So the expressions we used, I am not spending time because of it's already 1.5 hours, we have to finish it. So these are the three forces, wettability, Marangoni and hysteresis forces. We have to see how it works. These are simple setup we made 10 years back, okay? And a lot of excitement after seeing the first result. Yes. Okay. So this is how it works. Okay. So you see the pitch 20 micrometer, pitch 50 micrometer meters are actually representing two structured surfaces. Okay. And we applied a very thin polymer layer of the order of 1 micrometer, right? Very smartly done. Okay. Then you see the difference. Okay. On a flat surface, the contact angle variation is okay, it is there because the chemical is present, so it should be there, right? You can see that yellow, golden color, right? But it is not that high. But in the case of structured surfaces with that represented by the different pitches, you see a huge change, right? Huge change in contact angle, and now you take the tilt angle is a measure. It's not a direct measure of hysteresis, but it will give you a clue about hysteresis. There is a reason why we use the tilt angle instead of hysteresis. Whoever interested, we can discuss later. So tilt angle will give you an idea about hysteresis. You can see in the case of that golden one, hysteresis is very high, right? And it is not changing much. It is changing, but it is between 40 to 45, 50, right? But you take the other surfaces, when it is below 32 room temperature, it is having a very high hysteresis. It tells you that it really spreads and you droplet want to stay there. And when it goes to the other temperature, the hysteresis is becoming near to zero. It's amazing, right? And you have a transition region. This is what actually we have the control. 2 to 3 degrees transition region, we can actually really work because the region well below the transition and well after the transition is not useful for us, right? Because there is no gradient exists, right? So we selected this transition and Banu did it nicely with this very simple experiment with water flow and all. Okay. So then we translate this into, this is the contact angle, I am not explaining it, and we translate into forces, different forces for the surfaces we fabricated for this purpose. You can see the net force is very high or above zero in that transition region, right? That violet color, right? It tells you that this color, this graph tells you that if you apply this gradient, the droplet is going to move, right? Because there is a positive force, right? It actually can guide, got the point. So you see the design parameter, right? How much effort, like how the workflow went, right? Agree or not? So that will give you the translation. So this is actually the result. And we can do many things by changing the gradient in temperature. We can actually control the velocity of transport because that directly connected to the contact angle variation. Okay. Okay, so then I would like to summarize my talk. I hope it is clear, right? And this is actually stimuli responsive. You can do with electric field. You can do with magnetic field also, temperature, right? Many external stimuli. Light is also an external stimuli. But the physics what we discussed remains same. We have to modulate accordingly. Okay? Anti-fouling, self-cleaning, all these things we discussed in the beginning itself. Transport, portable lab on a chip device, one group. Some is doing amazing is Suman Chakravarti sir's group in IIT Kharagpur, whoever interested, they really go to real life applications as well. So with that, a lot of applications are there. I would like to conclude my talk. Okay. I hope now we understand, the importance of the wettability, and it is not like obvious, right? We have to go deeper and got the point. And it is like very rapidly developing and useful field. Got the point. It's one of the active areas in the case of soft matter, because it's highly interdisciplinary. Physicists alone cannot do, chemistry people alone cannot do, engineering people alone cannot, biology, because another important application is like wettability gradient means more wettable means biological molecules will be more happy. So a lot of biological applications as well. We did that as well. We have a paper with Vinod sir, yeah, your boss, in soft matter we published, right? So depending on your, as Damien told in the previous lecture, you can mold yourself. Soft matter is actually a good foundation you can actually align to the area of interest of yourself. Okay, with that, it's already 2 hours, I think, right? Close to 1.5 hours, right? Okay, 1.5 hours, good enough. Thank you for your attention. Any questions? Let us discuss. Ah, yeah.
Like pi r square gamma.
Yeah.
Gamma is the surface
Surface
energy. And what is r is the radius of the
Radius,
droplet.
base diameter. It is not the,
It's not a perfectly spherical.
no, it's the contact.
So
Base
the
diameter.
diameter.
Base radius. It's not the radius of the drop when it's in a pendant shape. It is basically give you how much surface area, right? Because it gives you the R square dependence, right? So how much is in contact will be given from that. That's a good question. Water drops, okay. So then some energy dissipation will happen in that directions as well. Because if you have like even your surface can be bit soft, right? If your surface is really soft, the droplet transport is not like this, because it will also try to bend to manage the energy balance. Okay, so it's different. Object is yeah. Okay. Okay. Elastic property depends on contact angle. You are saying about contact angle, right? So he's asking you any viscous, the elastic properties. The contact angle is anywhere dependent. I don't think it. To my understanding, till now, my research, based on my research, I haven't seen any direct connection. Connecting to this. Okay, but that could be one way we can think. But I have no clear answer at the moment. Okay.